Okay, so this is the next video of examples in the related rates section. So the last video ended with this example, which was the train pulling away from the depot example on the sheet. So let me flash over to the sheet for just a sec. So we're working through this this handout here. And like I said, the last video was mostly us doing this last problem, which, certainly took some time, no doubt about that. But you'll get quicker with these, or we'll get quicker with these, I should say. But that was a good starting problem because it kind of more or less involved most of the types of things that you'll have to do. And really the only thing that's different from problem to problem is just exactly what are the details of this one, what's the overarching fact that's connecting the quantities in the problem, and we'll see other examples of that in these next few. So on to number 2 then on the handout, which is this problem with bacteria, and then we'll move on to number 3 in this video, which is this problem with a cone. I may or may not have time to do 4 and 5 in this one, in which case I'll make a separate video for 4 and 5. But so we're on to this one, which says you're growing bacteria that grows in a circular colony, or grows in the shape of a circle, and we know some information about how the radius of the colony is growing, or that r of t, which is 2t squared there, is how big will the radius be after t days. Okay, and then it goes on to ask us a whole bunch of questions, and so, well, let's dig right in. So so first things first, with any of these problems, as always, as recommended, it's not a bad idea to draw a picture of the situation to at least get our thoughts organized, and maybe label it with some things. So in this case, so I guess this is number 2 on our sheet. What is our model here, or what is the thing that's happening is, well, we've got a circle, right, and it's growing. So this isn't going to be a very elaborate picture, but well, there's our circle. That's our bacteria that's growing. And in particular, what is the only quantity that we're really talking about in this problem is, or one of the quantities, at least that I can label, is the radius of the circle right there in my picture. And again, in trying to think about labeling, what do I label this? What do I label things with? Well, things that don't change, I can label them with the numbers that they're equal to. But in this problem, everything is changing, right? The radius of this colony is certainly changing because, look, you have a function for it. So it's certainly changing over time. It's different depending on what time we plug in. And of course, that's going to cause the size of the colony to grow. If the radius is growing, then that means the area of the colony is growing. So everything here is pretty much changing. So, and there isn't a whole lot for me to label in this picture, but I guess the only thing I'll label maybe is r of t for the radius at time t. And actually, I actually know what that is. It's 2t squared, but I'll leave that out for a minute and just say that's that, r of t. Okay, and there's a little bit of an art to this, I guess. If you kind of scan through the questions that are below, they mostly are all just talking about the interplay, if you just read them very briefly. They're mainly asking you about the relationship between the radius and the area of the circle, right, or the area of the colony. And okay, that's pretty much what all of these questions are all about. So, hopefully you have some understanding in some sense that the thing that I'm trying to probably tie together here would be the area of this circle and the radius of the circle. So, even if you don't want to label it, you don't have to, right? But I just maybe want in the back of my head be thinking about maybe that A of t is, of course, maybe the area at time t. Right, so maybe I just want to, there isn't really anything to label in the picture, but I'll just sort of write it down to remind myself that that's also sort of one of the things that looks like it's involved in this question. Okay, so like I said, there's a little bit of an art of maybe looking through the whole question first, just to get a sense of what is this question in general about. And I tend to probably not do that because I wrote the damn question, so I know what the problem is about. But you should maybe scan through the whole thing and say, okay, this seems like there's questions about the radius and the size of the colony or the area of the colony. So, all right. So step one done. In this case, step one's pretty lame. There's not a whole lot to say, and the picture is not terribly enlightening or revealing. So, all right, let's immediately move on to step two. Step two asks, do we have a fact that ties together the quantities, the changing quantities in our problem, some sort of a formula or something? In the last example with the train leaving the depot, Pythagorean theorem was a perfect connector because it connected together the sides of a triangle in an overarching fact that says a squared plus b squared is c squared. Well, in this problem, I don't have a triangle, I don't think, right? I've got a circle. And if I'm trying to think, well, what is the problem about? The problem's about the area of the circle and the radius and the relationship between them. So hopefully it's kind of screaming at you, right? That what is a fact that ties together the quantities in my problem? Well, I have a formula for the area of a circle, right? So that would certainly accomplish the goal of tying together the quantities in my problem, which are area and radius, right? So I think my overall, my master equation, right, or my master fact is that I know the area of the circle at time t should be, what? Circle is pi r squared, right? So pi times the radius at time t squared. So my overall fact, my overarching fact, or my master equation, I think is that. Again, how do you know if you have it right? Well, it should be an equation, which it is. I got an equal sign there. And it should tie together the quantities in my problem that I care about. Well, I care about the radius, and it looks like I care about the area. So, well, you know, that's what I've got, right? So that seems pretty good, I think. All right. Now, there's a number of ways you could go with this problem, I'll be honest. And I'll try to proceed in the way that I think is the most beneficial to you all. But I'll at least make a comment maybe at the end that there was maybe an alternate way to go that, you know, some of you might have seen and maybe would have actually been easier. But that's all right. Let's not do that. Let's just say I'm going to proceed with my steps. Okay, so step one, I drew a picture. Step two, I wrote down a connecting fact. Step three is to start looking at the questions and say, okay, let me try to start answering questions, and at some point I'm going to need to take a derivative, and that's that is the main action in step three. So, but first I might have some lead-up questions. And so let's see what I've got. The first question says, how long is the radius on day 3 or after day 3? Okay, so part A. Now, I try to help you out here in many cases to try to give you some softballs, right? Some easy questions to get you thinking about the problem. I really probably mostly care about the very last question in part B. But let's start with just part A. So part A says, how long would the radius be on day 3 or after day 3? Now, you don't need a whole lot of smarts, and you certainly don't need a lot of calculus. You don't need any calculus to know the answer, because look, we have an equation. We know that r of t, it tells us in the problem, is 2t squared, right? So the radius at time t is 2t squared. So this first question is very easy. This first question is just asking you, what's r of 3, right? What's the radius after day 3? Well, 2 times 3 squared, or 18, I think would be our answer, millimeters. Done, right? So you've at least got some points for this problem, right? That's hopefully that's a given. And then the next question is pretty easy too. So what's the area at day 3? So sorry, this whole problem is asking you about what's happening after day 3. So the second part of this is just asking you, so tell me about the area on day 3 or after day 3. Well, this is also pretty simple, I think, right? The area on day 3, well, the area on any day is pi r squared. Well, you just told me, or we just computed, that the radius on day 3 is 18. So if I do pi times 18 squared, that should give me the area of the circle after day 3, which again, I know that the radius is 18 because I just computed that. Okay, so if I do 18 squared, that's 324. And then if I do times pi, and your calculator has a pi key, that you can use, or you can just use 3.14. That's fine too. We're not really looking for super official answers here. I get about 1,000, and I'll just round to the nearest unit. You get about 1,018 square millimeters if you compute that. Okay. Now, the last part of this question, or the last part of this part, says, so if one single bacteria cell needs 8 square millimeters of space to live in, then about how many cells do you have after day 3? So again, you have to just sort of use a little bit of critical reading here and say, well, this is how much space you have after day 3. Well, if each cell needs 8 square units of space to live in, how many cells do you have? Well, so the number of cells after 3 days, well, that should just be how much space do you have, and each one of them needs 8. So if you divide by 8, I mean, that should tell you approximately, you might have to round, but that should tell you approximately how many cells are living in your little petri dish or whatever. And you get about 127 or 128. I'll round down and just say 127 cells. Okay, and in all likelihood, that's probably, as a scientist, maybe more of what you're interested in knowing is how many cells do you have, right? That's probably a more useful piece of information. So approximately 27. Obviously, you don't know that exactly because maybe the cells left some empty space in your area, but well, who cares? That's for the scientists to figure out. So, all right, so that's the end of that problem. Now, I mean, again, how much, I mean, I didn't use any calculus. I didn't even think I used any pre-calc, right? This is just algebra so far. But hopefully it kind of warms you up, right, and gets you thinking a little bit about, oh, okay, what are the quantities in this problem? And what do they represent, and things like that. So, all right, so part B, which I'll sort of start down here, and maybe I'll continue it up in my clear space over there. So part B says, okay, what are some other things I want to know? I want to know when, so what time, is the radius 50? When is the radius 50? Okay, so, well, that's the equation of the radius at any time t. So I want to know what t is that 50? Well, I have a whole lot of things to try here. So why don't I just plug in 50 for the r and solve for t, right? That should tell me the time when r would reach 50, sorry. Okay, this is pretty easy, right? I get 25 equals t squared, and I don't even need a calculator for that one, right? The square root of 25 is 5. So 5 is the answer. That is the time when the radius reaches 50. Okay, so another way of saying that is what? R of 5 is 50. If you want to say that, you could say that too. Whatever, however you want to say is all right. Okay, that answers that question. Again, don't overdo it, right? If I do you kind of the favor of asking you a bunch of easy questions first, just do them. And at some point, you're going to get to the point where you say, uh-oh, this is no longer easy. And, well, maybe we've reached that moment. So how do I know that? Well, so what does the next question say? The next question says, at what rate, at what rate is the area of the colony growing at that time? In other words, at time 5, I guess, right? That's what we just computed. Aha. Okay, so how do I know, or how do you know that you need the big guns, I guess, right? This question is asking me about the rate at which the area is changing. Okay, it's pretty much a given that if they're asking you about the rate of something, you probably don't immediately know that. These other, however many, 4 questions I answered, mini questions I just answered, nowhere did you see the word rate in there at all. Now I used some things, but I nowhere in there did it ask me at what rate is blah, blah, blah changing. So I was able to probably get by, just on basic algebra and answering those questions, which is what happened. But this problem is asking me about the rate at which the area is changing at time 5, basically, right? So again, it's kind of helpful. So this is part B continued over here. I'm going to come back up to the top here now. I'll call this part B or b part 2 or something. That's b part 1. Is to say at what rate, right? At what rate is the area changing? So what is it that I'm looking for? I do think this is important. We're looking for the rate at which the area is changing. So the area is A, and it's the rate at which the area is changing at time 5. That is what I'm looking for. A prime of 5 is what I'm trying to compute. Okay? All right, so to try to help you out here, right, how do I know that I'm supposed to do what I'm about to do? It's because the thing I was looking for involves the derivative, right? Nowhere did I need that before, so I didn't need to compute a derivative because don't do things unnecessarily, right? But now I need A prime. I need A prime, and I don't have A prime. I have a very nice equation for A, but I don't have an equation for A prime. And so I better do that, otherwise, you know, I won't be able to ever evaluate and figure out what A prime of 5 is unless I have an equation for A prime. And the only way that we know how to introduce derivatives is to take the derivative of our master equation. So I'm going to now compute, just like I did in the problem before, I'm going to compute the derivative of both sides of my big fact here. And I'm always going to ask myself, for each term that I see, what is the derivative of this? Or what is the, you know, what can I say about the derivative of this? Okay, so the left side, I have A of t over there. So the question is, well, what's the derivative of A of t? Well, I asked you this question it's been a couple of videos ago, right? When we started talking about implicit derivatives, the very easiest question, which sort of is like a smart-ass answer, I guess, is what's the derivative of A of t? Well, I don't know, of course, but it would at least be, it'd be A prime of t, right? That would be the derivative of A of t, would be, well, A prime, right? Because that's the definition of what the derivative is. So that's what I'm going to write down. It's always a little bit sort of like, shouldn't you be able to say something else, or that's not really an answer? Well, I mean, that's kind of true. It isn't really an answer, but what else am I supposed to say? I don't want to make something up here. So what's the derivative of A of t? A prime of t. That's true. It is the derivative. Okay, now how about on the right-hand side of my equation? So I've got pi. Now pi is a number. So remember, coefficients, when we do derivatives, coefficients just come along. So pi stays there. And then what else do I have? I have r of t squared. Well, what's r of t? What's the derivative of r of t squared? Well, we've done this one. Again, look back into the video with implicit derivatives. We did it for a of t squared. Well, r of t squared, it's the same thing. So I should get 2 r of t times r prime of t. Okay. Now I don't know why. So that's what I would get, right? Because again, we've done this one a couple of times now, right? The derivative of a function squared is 2 times that function times the derivative of that function. Now, and again, that comes from the chain rule. So come off to the side here if you want and do what's the derivative of r of t squared, and do the chain rule if you want. I won't do it for you here, but that's what you would do to figure out, oh, okay, it's 2r times r prime, or 2r of t times r prime of t. Okay. Now, why don't I get that on the left-hand side? I often have students that will write that the derivative of a is 2a times a prime. In other words, you know, make it look just like that, but with a's instead of r's. But that's not right, because this is a of t, and this is r of t squared. Okay? So the square makes a big difference, right? The square says, oh, this is legit a chain rule now. But just a of t by itself, that's not a chain rule. That's not a function plugged into another function. That's just a function. So what's the derivative of a of t? A prime of t. But the derivative of r of t squared, that's legit a chain rule. So I need to do the chain rule, blah, 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 and that's how I get that. Okay? All right, so in any case, this is the derivative. I've computed the derivative, and that's what I've got right here. And again, what should you be thinking about? This is now my new, or an alternate version of the master fact. But now it's a fact that involves derivatives, right? You see the derivatives are all over this problem. Okay, so but it's still sort of a master fact in that sense that it's true at any time t. Anytime you want to know about, here's what the derivative is. Here's a fact, and it happens to involve a prime and r prime. Okay, so after you take the derivative, you're free now to say, okay, the question was asking me about a specific moment in time, and in particular, this question is asking me about what's happening when the radius reaches 50, or in other words, or it's asking me what's happening at time 5. Okay, now we agreed a few minutes ago that I'm looking for a prime of 5, but that's pretty good for me, I think, right? Because look right here, I have a prime, so that's good, and I hope that maybe I know what these guys are at time 5. Okay, so what is it that I'm going to do now is I'm going to plug in time 5, because that's the specific moment that the question was asking me about. It said, what's happening when the radius is 50? Okay, but we know that the radius is 50 at time 5. Okay, so that's what it's asking me to do, so that's what I'm going to do. I'm going to plug in time 5. Again, this isn't magic. I didn't just randomly know to do that. I looked at the question. The question said, tell me what's happening when the radius is 50. Well, once I compute the derivative, which is what I did in this step here, that's true at any time t. Well, now I don't care about any time t. I want you to tell me what's happening at time 5. So I'm going to plug in time 5. So I get a prime of 5, which that's good because that's what I was looking for, right? Okay, pi is just pi and 2 is just 2. Now, r of 5 should be the radius at time 5, which is 50. Okay? So that's 50. Now, r prime of t, I don't actually know what that is, right? I mean, I'm looking at my screen here, and you look at your screen. I don't see r prime written down anywhere except, right here. So I need to know what that is. And here's where you're going to encounter things that you've not seen before, but don't freak out. What's r prime of t? Well, it's the derivative of r, right? That's what the little prime mark means, right? The little tick mark means it's the derivative of r. Do you know what the derivative of r is? No. It's nowhere on my screen. But here's where you have to use your intelligence and say, but wait a minute. R of t is right here. It's 2t squared. So how hard is it for me to write down what r prime of t is? Super not hard, right? It's 4t. I mean, right? It is. So what's r prime at time 5? Remember, I care about, right now, time 5. 20. Right? Just plug in 5 for t. 20. Oh, well, look at this. I now have a prime of 5, and those are all just numbers over there, right? In fact, it's what, 2,000 pi? What units do we have? Square millimeters. Okay, so, and that's what, 6,000-ish square millimeters of space. That's the rate. Oh, I'm sorry, it's a rate here, right? It's the, 2,000 pi square millimeters per time, which time for us in this problem is days, so per day. Okay, so the rate at which the colony is growing at time 5, or in other words, when the radius reaches 50, is that it's growing at a rate of 2,000 pi square millimeters of space per day. So that's how much space is being added per day to the colony. Okay? Which I could have done this at the beginning of the problem, but I'm just going to draw you a small picture here. You don't have to write this down, but of course, when a circle grows, right, kind of grows in rings, right? So as a colony grows, right, as the radius grows from that to that to that, you're adding an awful lot of space, right? Because you're basically adding a ring. So as the radius, as the colony grows, the amount of space you're adding each day, in this case it's per day, is increasing. So it's reasonable to ask a question like the one I just asked, because it's not always going to be 2000 pi every day. Because of course, as I go through time, as I add a little ring around the edge each time, that ring is getting bigger and bigger each time. So if I asked about a prime at 10, time 10 instead of time 5, you're going to get a much bigger number. Okay, but that's kind of neither here nor there right now. Okay, and now I'm almost done. The very last question, I guess B part 3, says, could you tell me the reproductive rate? Now I should probably clarify. What do I mean by that? I mean how many cells per day, not space per day, but cells per day am I adding? In other words, how many new cells are, created or born every day at this time, or per day at this time? Well, that's just going to bring us back to the fact that we know that in terms of space, each cell needs 8 square centimeters of space. Sorry, square millimeters of space. So if I take my answer here, 2000 pi, from the last part, and if I divide that by 8, that should do this conversion for me to be able to say, okay, well that should tell you then how many actual cells you're adding per day at this time. So if I take 2000 times pi and then divide by 8, you get, I'll just round it to the nearest cell, about 785 cells per day. Okay, so which again, you can imagine that again being a very important number to be able to compute, because you've got some sort of a boss telling you need to, whatever, the productivity needs to be blah, blah, blah per day. And how many cells per day are you adding? Well, this tells you exactly how many cells per day you're adding. Okay, so that's that problem. I'm just going to make a comment here at the end. At the very beginning of the problem, the fact that we knew what R of t was means if you were thinking this, you were right. You could have just plopped that in right there and said, I'm not going to worry about R of t throughout this problem. I'm going to immediately from the get-go replace it with 2t squared. Then you could have proceeded through the problem just like it was a regular derivative, and you wouldn't have needed all this implicit stuff. I'm going to be honest, it doesn't really save you that much time, and in many ways I think students find it more confusing to try to juggle more than one way to do a problem. So I would say you're better off doing it the way that we just did it. And it also is better in terms of giving you a more representative and broader example rather than something that will only work sometimes. So I'll just say that and stop talking about this problem. So that's that one. I think I have time, and might as well go ahead and do the next one in this video, and then I'll stop before doing the last couple problems. Okay, so the third problem is also a geometry sort of problem, but uses volume instead. So let's read this one. So it says you've got an upside down cone, and water is pouring into the cone at a rate of, it says, 9 cubic feet per minute. Okay, so that's some sort of a volume, I don't know how many gallons that is, but something, it's something like that. And okay, we know that the cone itself that is being filled up has a height of 10 and a radius of 5. Okay, and the question asks, so now this is one of these where I'm not giving you the lead-up questions. I'm just asking you the question that I care about. So we're going to have some side problems that we're probably going to do along the way. But that's all right. So the question says, at what rate, okay, where it says, how fast, okay, fast is a rate, how fast is the water level rising when it reaches 6 feet? Okay, and I tell you that the volume formula for a cone is 1/3 pi r squared h. Okay, so this is one where I think we do need a picture to really get a sense of what's happening here. So I'm going to draw that first. So I have a cone, and it's upside down, which means that it's like an ice cream cone. The pointy end is at the bottom. And let me draw that. So first of all, okay, I've got a cone. And the cone itself, right, the shell or whatever this is made of, is 10 feet high by 5 feet wide. Okay, I'm sorry, the radius is 5. So what does that mean? That means that in the cone itself, that's 5, and this is 10. Whoops, let me do it this way. So it's okay for me to label that 5 and 10. Remember, what my labeling rule is that things that change, I should label with functions. Things that don't change, I should label with numbers. Well, that doesn't change, right? The cone itself is not a magical cone. It's always 5 by 10. Okay. Now what is changing is that I'm pouring water, right? Water is pouring into this cone. Let me, erase that 3 just because I need that space. Water is pouring into this cone, and maybe so I don't forget that it's there, I'm going to write it up here, at a rate of 9 cubic feet per minute. Okay, that's the rate at which the volume of water is being poured in, which means, of course, that something in my problem is changing. Namely, this cone is filling up, and it's filling up with water, and that is a quantity that I also want to depict in my problem, and that is a quantity that's changing. So I'm going to do, like we learned in elementary school, draw the water level with a sort of wavy thing, right? Now that's moving, that's changing, because water is pouring into this cone, it's filling up, right? So that's changing. So in particular, the height of the water, which maybe I would draw in like that, that's changing because it's rising. And even the radius of the water, which I might just sort of draw with a fat line like that, that's also changing. Because right, what happens when you fill a cone? The radius of the water line, or the water level, is very small when you start. But as the cone starts rising, or as the water level starts rising, the radius of the water, top of the water is also growing, right? It's getting wider. Okay, so these are both changing. So I should fill them in with or I should label them with functions. So how about I call that R of t for radius at time t, and how about I call that H of t for height of the water at time t. Now those aren't 5 and 10, right? 5 and 10 are the overall size of the shell, right? The shape that we're filling. But R of t and H of t represent the radius and height of the water level at time t, and that's changing. Okay? So hopefully that's not a huge leap of faith yet. And again, in scanning the problem, what seems to be my other characters in my story? Volume, right? If we look at the problem, what is it all talking about? It's talking about the height of the cone, and the height of things, and the radius. Okay, I got that. But it's also talking about the volume of water in there. I know some facts about that. In particular, the first fact that they give me describes how does the volume of water change. So volume seems to be a character here. So just for my own just sort of sanity, I might remind myself that V of t, which might be the appropriate letter, is the volume of water at time t. Okay, it's not really it's not a label, so to speak, but it's just sort of a player. It's a character in our story. So I'm going to write him down up there just to have him be on my paper here. All right, so step 1 done. I've drawn a picture, I've labeled it, and I'm on to step 2, which is to say, can I write down a fact that ties together the quantities, the changing quantities in my problem? And okay, and again, we kind of mainly have 3 different types of things. If you have a triangle, you probably want Pythagorean theorem or trig. I don't really have a triangle here. I sort of actually do at the bottom there, but that's not really what's at play here. What is at play here seems to be the relationship between the amount of water in the cone and how the height and the radius are changing, right? That's kind of what these questions are asking. Well, there really is only one question here. How fast is the water level rising when it reaches 6 feet? So it seems to me as though this water, right, the water that's flowing in, is the sort of main thing that's changing, right? So I want to see, how can I write down an equation that relates the water with the amount of water with the height and the radius and things like that? Well, hopefully this one's kind of staring you in the face. I have a volume formula, and in fact I gave it to you in the problem. That's a very nice overarching fact, right? Because why? Because that ties together the quantities in our problem in a pretty nice, neat way. So I think my master equation, or my master fact that I'm going to use, is just simply the volume formula, which says the volume at time t, how much water is in there at time t. Well, the volume of anything, any cone, is always 1/3 pi r squared times h. But remember, in our problem, r is changing, so it's really r of t squared times h of t. Okay, and again, this serves just to say that the volume of water at time t is the radius at time t squared times the height at time t times 1/3 pi. Okay? So all of those have the function, right? They're all functions because they're all changing over time. But as an overarching fact, that's always true. The volume at time t is 1/3 pi times the radius at time t squared times the height at time t. Okay? So hopefully that's kind of clear that that's my overarching fact. Now I could have asked you some lead-in questions, things like, when the radius is 2 and the height is 4, how much water's in there? Or I could have asked you, at what time does the volume of water in there reach 100? Okay, and I could have asked you those sort of standard lead-in questions. It would mainly involve you just using the master fact and solving for one of your unknown quantities. And it wouldn't have involved a derivative or anything like that. But I didn't ask you those things. Instead, I just went right to the main question, which is how fast is the water level rising when it reaches, when the height of water in there is 6 feet? Okay. So again, I should probably have at least in the back of my head, and it wouldn't hurt you to write it down even, what is the thing that I'm looking for? What is the thing that the question part of the question is actually asking me to compute? So let's look at that. It says how fast. That's a rate, right? Speed, right? Fast. So at what rate is the water level rising when it reaches 6 feet? Okay, so it's the rate. So I'm immediately thinking derivative, I hope. It's the rate at which the water height or water level is rising when the height of the water is 6 feet. So I'm going to put it off to the side here. So I'm looking for the rate at which the height, or the water level, right, is changing when the height is 6. So this is a slightly different question, or a slightly different way of asking the question. I don't know t, right? I don't know what time this is going to happen. I could probably figure it out, but let's not. Okay, I am being referred to a specific moment, right? When the height of the water is 6, that's a specific moment, right? That's literally an instant when in the process of this water flowing in. At some point, the water height will be 6. That's the moment I care about. Now, it's true. I don't actually know that that's at time equals, 7 or something like that. I don't know when that happens, but that's all right. Let me just roll with this. If I need to compute the time, I'll do that later. But this is okay, right? This is my thought bubble, right? I'm looking for h prime when the height is 6. In other words, I want to know what is h prime when h itself is 6, or when h of t is 6. Okay? So for sure I need h prime. That's a given, which means I need a derivative. right? That's the only way I can ever introduce a derivative, is to take the derivative, as I've done now in the last few problems, of my big master fact. But I'm going to throw on the brakes right now and say, uh-oh, all right, I guess. That's the cleanest way I can say that. So let's just use a little bit of intuition here, right? I think I'm okay with what's the derivative of v. Well, this is just like the last problem, right, where I said, what's the derivative of a? Well, it's sort of a smart-ass answer, but, well, a prime. Well, what's the derivative of v? V prime. So far, so good. But, okay, and 1/3 pi, that's all right, because that's just a number. 1/3 pi is just a number. It's a little more than 1. So, okay, that's a coefficient, so that just comes along. But now I'm going to ask you to think for a moment. What's the derivative of that? And here's where you should become very concerned, because what is that? Well, it's the product of two things. It's r of t squared times h of t. Oh, so that's a product rule. Ugh. But even worse, r of t is also squared, which means that would be a chain rule. So you've got a chain rule inside of a product rule. Now, I'm not going to say that this is impossible, but I'm also going to say I hope we have nothing to do for the next half hour, because that's how long it would probably take you to chase through all of this. So in moments where you kind of see yourself maybe going to a very dark and sad place in a problem, it's not a bad idea to throw the brakes on. Now, again, I will confess that I am at the advantage of already knowing how to do this problem, so I knew to throw the brakes on right here. But even if I didn't, and I'm you right now, when you kind of reach a point where you're like, this can't be right because it's just kind of messed up, you're probably right that it's not right, and maybe there's something else I could do. So I'm going to throw the brakes on, and by that I mean erase, and not do that just yet. And let me identify my concern. My concern is that, just like it was with optimization problems, I have too many variables here, right? In optimization problems, that was always a bit of an issue. Now, it's not as much of an issue with related rates. You can have more than one, but I'm really not happy about having to do a product rule and a chain rule right there. And I'd be much happier if I could maybe get rid of R or get rid of H. In other words, do a substitution. Remember, the substitutions are your friend, and they're always going to turn a more complicated equation to an easier one. So I'm very interested in trying to make this a little bit simpler. Now, where do I see a substitution? Well, I'll be honest, you're going to have to stretch a little bit to see this one. So I would point this out to you, and I would probably call your attention to this. I wouldn't expect you to just see this. But let's look back at our picture for a second. Just by using the old SAT Kaplan test prep course thing, I haven't used 5 or 10 yet, right? These two. Well, they probably told me that for a reason, unless I'm being a jerk and just giving you extra information. But no, I did tell you that for a reason. Why? What do you notice about 5 and 10? And this is where usually somebody, after a couple of wrong answers, says, 10 is double 5, or 5 is half of 10. Now, squint with me here for a second. As this cone is being filled, right, and the water level is rising, each one of these sort of mini cones inside of the big cone is the same shape. It's just a mini version. Yeah, hopefully you can kind of see that. Or maybe you played around with something like this before. So in the big cone, notice, in the big cone, the radius is half of the height. Right? 5 versus 10. Or you could say the radius, or you could say the height is double the radius if you want. But the point is that that's actually true throughout the cone, not just the big cone shell, but even these little mini cones that I'm forming when I fill with water, they also satisfy this proportion, that the radius is actually always half of the height. oh my goodness, well, that looks like a side fact. And a side fact that would be perfectly wonderful to fill in right there. Because why? That's going to get rid of R, and instead I'm just going to have H's, which is very good, because it's going to just make the derivative a lot easier to compute. Okay? Now, I guess the question is, do you get rid of R, or do you get rid of H? And here it's actually very important to do the right thing. I'm choosing to get rid of R because my questions are all about H. If I get rid of H, I'm probably not going to be able to answer this question. So rather than getting rid of H and converting to R's, I'm going to get rid of R and convert to H's. Okay? So sort of a pre-step before I do the derivative is to do a little bit of just simplifying or substitution. So instead of R, I'm going to do 1/2 H because I can, right? Because it's the same thing. I use my substitution down here. Okay, and then let me just do an algebra step here. If I do 1/2 H squared, you square both of them, which means 1/2 gets squared. 1/2 squared is 1/4. And 1/4 I can put with 1/3 to make 1/12. Okay? And then what else do I have? I have H squared and another one, which makes H cubed. Okay? So that's just algebra. Okay, now I'm going to do my usual step, which is to take the derivative of both sides, and then I'm going to plug a bunch of stuff in. Now, just like I said before, what's the derivative of V? V prime. Done. 1/12 pi is just a number, so that comes along. It's a coefficient. And now I need to do the derivative of h of t cubed. Now, that's an implicit derivative. So do it just like we did a of t squared at in the 2 videos ago when we did implicit derivatives. Do the chain rule. Here, I guess I'll just do it since I'm already almost done. What is that? That's h plugged in. Sorry, that should be h of t. Plugged in to the t cubed function. What's the derivative of t cubed? 3t squared. What's the derivative of g? Well, I don't know, but it's the derivative of h because g and h are the same. And now if I put my pieces together, I should get f prime with g, which is h, plugged in, times g prime. So I should get 3h squared times h prime. Okay, do that slower and mimic what we did in the implicit derivative section if you need to see that a little bit more carefully, okay? But that's the derivative of h cubed. Okay, so I'm going to write that down right here. 3h squared times h prime. Okay, and let me do one algebra simplify here. I've got a 3 and a 12, which I should be able to cancel that and make it 1/4, right? 3 on the top and 12 on the bottom is really 1/4 pi now. And what am I left with? H squared times h prime. Okay, now this is true at any time t. So in particular, at the moment in question, this is also true. Now, what is the moment in question? Well, the moment in question is way up here in the corner, right? The moment in question is when the height of the water reaches 6. That's the moment in question. Well, when does the water height reach 6? I don't actually know what time that happens, but I do know that at this moment that I care so much about, I certainly know that the height of the water is 6. So when I'm trying to do my plug-in step, so I want to always plug in values about the moment in question, which is when the height of the water is 6. Well, what is it that I need to know? I've only got 3 quantities here, these 3. This is the one I'm looking for, because I said that already up here. So that one's going to stay. H, well, the moment in question is when the height of the water is 6. So how high is the water at the moment in question? Well, 6. So fill that in. Okay. Now what's V prime? Well, V is the volume, right? V is the volume of water. So V prime is the rate at which water is being added. Well, I have to sort of scan my problem for a minute. I don't immediately see that. But then maybe if I look back at my picture, remember, I was told water is pouring in at a rate of 9 cubic feet per minute. That's V prime. And in fact, it's always, so it's flowing in there at a constant rate, right? So it's like you turn on the faucet and then you say, okay, go, right? So it's always flowing in at a rate of 9 cubic feet per minute. So V prime at any time is 9. So in particular, at this time, it's 9. Okay. So sometimes it's always almost a little surprising, but this is actually wonderful because this is the only thing I don't know. Everything else in my problem is a number. Okay? So I'm going to solve here. So 6 squared is 36, right? And 36 divided by 4 is 9. So you actually just get 9 equals 9 pi times h prime. And so if I divide by 9 pi on both sides, I'm going to get 9 over 9 pi, or 1 over pi if you want. So I get h prime is 1 over pi, which you can write a decimal if you want. That might be somehow a little bit more informative, I suppose. So if I want to, I can say what's 1 divided by pi. And you get about, if you want, about 0.32 or 0.31 feet per minute. Okay, so about 1/3 of a foot or so per minute, which is what? 1/3 of a foot is 4 inches, is that right? So at about 4 inches per minute is the rate at which the water level is rising at this time. Now again, if I had asked you what's happening at the beginning when the water level is really low, well, if you've ever filled up any sort of a shape like this, right, the water level rises very quickly when it's almost empty. But the water level rises much more slowly later on. So when the water level is way here at the top, it's only creeping up at a very slow rate. So this number, 0.32, it'll be a much larger number if I asked about down here, and it'll be a much smaller number if I asked about up here. But in any case, for whatever reason I care about this, that should be the answer. Okay, so hopefully you're kind of getting the rhythm, right? I mean, you can almost, I don't know, hopefully you can kind of detect it. It is the same rhythm for all these problems, but yes, there are subtle differences between each one, and yes, there are some tricks. This is one I would say I would sort of, I don't know, I would steer you in that direction at the very least. That's a tough one to just sort of spot out of nowhere, right? So I would clue you in on that. But the rest of it, I think, is a very fair and reasonable question. And again, ones that are like these or ones that kind of use this general idea are also, I think, good. All right, so that's the end of this video. There's a couple more examples that I'll do in the next video. In particular, I've yet to do one that involved trig, so I mainly want to do one of those for you. And then you should try them, and then you should try the homework problems that are going to be posted, and see how you do. Really try them as hard as you can without looking at the answers. There's almost zero value in just reading through my answers because they're probably going to make sense, or I hope they do, but that's pretty much not helpful at all, because you have to be able to do all of these steps on your own, without any sort of coaching and things like that. So anyway, so stay tuned for one more video which involves angles and trig with these related rates.